Thank you po.
Hi, good evening, Doc.
Good evening. Happy New Year.
Hi, Happy New Year also.
Hi, Sir Josh, next sem, second sem.
Can I become the host of this meeting?
Mga pang-graduate po, pwede hindi dito, pwede po mga college po. At iba.
So, good evening, everyone. Yeah, thank you for joining. This is Plan 252. Okay, so um, transport modeling. Yeah, welcome back. Okay. Happy New Year.
Happy New Year.
Uh, before you start with your presentation, I would like to uh, show certain things. So our schedule for this is the plan for today. So our schedule next week you will have the final exam. Okay, the material is from midterm, right? And today you will have your project presentation. So please submit your paper if you have not done so, and then also the presentation slide in Moodle. Okay, and then now if I know some of your group may have some problem between, the members, so please resolve it on your own first. Okay, and then today's presentation. Today I will discuss about network optimization. Yeah. Okay, so before that lecture, I would like to invite you to the project presentation. Yeah. So who will do first? See, got this piece maybe. Yeah, to do first. With there is you as a host.
Yes, again.
Go ahead.
Thanks, sir.
Follow.
Sir, good evening, sir. Happy New Year. And Happy New Year to everyone in the room. So, we are Cardis Beast, and our group is composed of. Sir, can you see my screen?
Oh, okay. Yeah.
Okay, sir. Thank you, sir. So, our group is composed of Bianca Luscusin, uh, Katrina Catimpo, and yours truly. And our topic is NLEX Harbor Link Decongestion Study. So, sir, for a quick background of our study, so the North Luzon Expressway, or the most commonly called as the NLEX, is the one of the road networks connecting Metro Manila to Central and Northern Luzon. So the other road networks is the MacArthur Highway and the Maharlika Highway, which is a non-tollable road network, and the NLEX is a tollable expressway. So within the NLEX, there is a two cloverleaf interchange connecting Metro Manila. One is the Balintawak interchange and the Harbor Link interchange. So the focus of our study is the Harbor Link interchange, and the Harbor Link interchange is one of the two cloverleafs of interchanges that serves access to Metro Manila, and it connects the northern provinces to Valenzuela, or their Barangay Karuhatan in the west side, and Quezon City, or their Mindanao, and in the east, and the Caloocan uh, area, or Balintawak, in the south. So we could see in the in the blow up image below, where's the location of the Karuhatan, the Mindanao, and the Balintawak area within that within the Harbor Link interchange. So for the problem statement, so the general problem of this Harbor Link interchange is that with the growing economy of the northern and central Luzon, and the port of Manila growing economic activity, uh, the Harbor Link interchange is the critical point of those two locations, because the port of Manila has direct access to this Harbor Link interchange. So if you're coming from uh, Port of Manila, you're going to the north, you will pass through this interchange in North Luzon Expressway. So as indicated in the image, the blue line represents the path flow of vehicles from the north port of the Port of Manila. It's in the Karohatan side going to NLEX North. So they have to do this path flow, so the blue line. So they have to use the southeast loop to go to the north. And then next is that it conflicts with the vehicles coming from the north going to the east side, going to the Quezon City side. So if you're coming from the north, the yellow path flow uses the southwest loop going to the Quezon City, or the Mindanao area. So this conflict creates a weaving section which reduces the capacity of the cloverleaf interchange and forms a queue of vehicles. So as you can see in the the sample photos below, so the queue, this is the current situation. This is just shot a few weeks ago. So this is the current situation of the Harbor Link interchange during peak hours. So there's a heavy traffic congestion and long queues in this portion. So for the objective of our study is to decongest the NLEX Harbor Link interchange by modeling possible countermeasures using ideal flow network. And the hypothesis of our study is by increasing the capacity and decreasing the demand of the interchange of the traffic flows, decreasing the demand, the traffic flow and the congestion levels will improve in this area. So for just a brief review of related literature regarding the cloverleaf interchange. So for the information of everyone here in the room, so interchange is a grade separated intersections to eliminate the crossing conflicts through vertical separations. As you may understand, in expressway, we have the priority of expressway is mobility rather than accessibility. So they have to grade separate a crossing interchange, a crossing intersect an intersection for them to reduce the conflicts, especially the left turning conflicts. So, and then the rationale for the cloverleaf design is it consists of multi-level interchange at which all left turning movements are performed using loop ramps. So the the cloverleaf interchange consists of 4 loop ramps in all 4 quadrants with no traffic control. The traffic control explained here is that there is no traffic signals, traffic signalizations, or any other uh, traffic control devices. So the purpose of cloverleaf design is to allow unhampered connectivity for all movements between 2 highways. So the 2 highways described here is the highways on the in the above and on the below. So for the methodology of the study, so we have gathered relevant traffic data or historical data, and then we have conducted traffic surveys. And then after reviewing those data and conducting the traffic survey, we analyze the data, we characterize the traffic composition that we have gathered from the data. We have identified the peak hour, and then we have developed the flow and OD trip matrix of the area. And then next, after generating the OD matrix, we have we did the IFN model, input of the road network characteristics, and input of the traffic data in the IFN model. And then the next, we have assessed the base scenario. So in the base scenario, we have identified the current level of service situation, and then we have identified the conflict points and bottlenecks in the interchange. And then after identifying those characteristics of the base scenario, we will formulate an alternative scenario or the improved scenario. And then we will analyze that alternative scenario, and then we will now test if it is effective or not. So if it is not effective, we will go back to the formulation of another alternative scenario, which could be an iteration of it, an iteration of that alternative scenario, or probably a policy introduction or other different kinds of improvements. And then if the scenario is already effective, then we go to the conclusion and recommendations. So for the traffic modeling tool, so we have used the GIS to model the road network model, and then we plot it in the traffic data. We call this the OD map, so we could see how many PCU of vehicles going through specific directions. And then next, we model it using the ideal flow network transport web. And then next is we assess the situation based on the outputs of the IFN and compared it to the standard LOS matrix from the highway capacity manual. So the inputs of the IFN, so as I have mentioned, the nodes and links are prepared using GIS. So in the IFN model, there's an available OSM map, but during our consultation with Prof and during our learning to use the program, the loop ramps, or not just the loop ramps, but the other ramps as well, are not modeled in the OSM. So we have used another GIS program, which is the QGIS. And then here is the assumptions that we have. Actually, this is not assumptions, but these are the the calibrations that we have used. So for the ramps, the capacity that we have used is 1,500 PCU per lane per hour, which has a speed limit of 40 kph. And the main carriageway or the main line of that expressway, we have used the 2,500 PCU per lane per hour, which has a speed limit of 100 kph. So this is expressway standards, and the values is we got it from the highway capacity manual. And then next, we input the flow matrix to calibrate the model, and then for the next. So this is the the flow matrix map that we finalized. So this is the flow for each of the direction of the cloverleaf interchange, and this is the OD matrix that we got. So for the peak hour, we have identified the peak hour of the Harbor Link interchange as the 10 to 11 in the morning, and then we have assessed from this OD matrix that the majority of the trips are from the NLEX North going to the NLEX South, uh, and then the vice versa, which is the mainline traffic, which is above 3,000 PCU per hour. So in terms of front volume, the high number of vehicles are using the southwest and the southeast Cloverleaf loop ramps, which is identified in the problem statement. So that is the 1,379 and the 1,069 PCU per hour. So for the base scenario here is BN for the discussion of the analysis.
Good evening, everyone. I will be presenting our base scenario assessment, including the first two alternative scenarios. For this, we use GIS for visual representation of the number of lanes, as you can see in the screen, and the congestion data based on the highway capacity manual LOS table. For the base scenario, this yielded an average congestion level of 72% or LOSC based on the HCM LOS table. However, scrutinizing the per link results, over almost 14 links got over 100% congestion level or LOSF. So we're going to have to improve the loops and the other weaving section, since those are the links that yielded LOSF or more than 100% congestion. Those identified conflicts will be the focus of widening for alternative scenario 1. Next slide, please. As discussed, this is the visual representation of the LOS congestion for the base scenario. As you can see, all the four loops have LOSF. The network suffered due to the bottlenecks caused by sudden reduction of lanes and the limited capacity of the loops, since they are all consisting of one lanes only, and the speed limit is only at 40 kph. Hence, they can only serve a limited number of PCU. Next slide po. These are the identified bottlenecks and weaving conflicts, which will be the focus of the widening for our first alternative scenario. Next slide. For our first alternative scenario, we are proposing lane widening for the identified conflict sections, particularly the loops, all the four loops, and the receiving links, including the weaving sections. We will be increasing the lanes of the loops from 1 to 2 lanes, and we'll be adding 1 lane each for weaving sections and receiving links to prevent the funneling due to the sudden decrease of capacity. Next slide, please. For the results, this yielded a better overall network performance of almost 48% or LOSA. However, 11 links are still experiencing more than 100% of congestion. With this, we will be assessing in the next slide additional widening to assess the further impact of capacity increase. Next slide, please. Wherein we added additional lanes to the identified conflicts. However, this only yielded to an increase of 7% if, of overall network performance. And most loops are still classified under LOSF. Only one loop i- is has a congestion of less than 100%. With this, we shall explore other countermeasures not limited to lane widening. Next slide. For alternative scenario 2, we are suggesting the bypass road from the west to the north, considering the high amount of traffic from the west or from the Karuhatan and Port area to the north, going to Bulacan, Pampanga, or the further parts of the North Luzon. This is to lessen the number of the users in the cloverleaf loops. Next slide. However, this bypass scenario yielded a higher resulting congestion level, which could be attributed to the increase in total flow due to the additional links introduced without increasing the capacity. With this, I will turn over the floor to Katrina for other alternative scenarios, which are not limited to physical interventions. Thank you.
Okay, good evening everyone. So since the two previous alternative scenarios may not be sufficient to solve the congestion in the network, so the first policy we have considered, or the policy we have considered, is congestion pricing. So we found related literature that said that congestion pricing in Metro Manila, so I think this is a Metro Manila study also, is expected to decrease traffic demand by 24%. So we applied this reduction to the traffic flows, and the result is in the next slide. So the congestion level of the entire network is at LOSA at 0.55. However, there are still links that remain LOSF, specifically the cloverleaf loops and the receiving links of these loops. So even if the overall performance of the network is good, some links are still left behind. And the maximum values for congestion, travel time, and delay are still extremely high. So next alternative, please. So for the fourth alternative scenario, we tried to combine the lane widening and congestion pricing. So it resulted in a network average of 0.34 congestion level, or 34%, which is equivalent to LOSA. So far, this is the alternative scenario that caused the most positive effect on the overall network performance. So this combination brought the network congestion levels below 100%. So as we can see in the table, so earlier some of the maximum congestion level are around 200, 300, which is very high, but right now it's already below 100. So as we can see in the visual representation here, the highest or the most extreme LOS is now at E. So also some of the cloverleaf ramps are also improved from red until to orange to yellow to green. So this, we can conclude that increasing the capacity and decreasing the demand for effective countermeasures. So next slide, please. So this is just a summary so we can see visually and compare. the LOS, the effects of the proposed countermeasures to the level of service. So warmer colors mean more extreme congestion, and those colors approaching green are improved conditions already. So the one on the lower right is the combined lane widening and congestion pricing. So this caused the most positive effect. So next slide. So for future studies, if we set the target congestion level at 0.8 maximum or LOSC, so these are the target values that we can try to achieve. So this can be used for future proposals or for future proposed countermeasures. So the maximum congestion is at 0.8, network travel time, and other parameters as such for this harbor link intersection. So based on the results of the previous alternative scenarios, we are still a bit far from
Hmm.
the 0.8 maximum congestion. So in the future or for future studies, more policies or countermeasures may be further explored in order to improve the results. Next slide. So here is the summary of our conclusions and recommendations. First is that the most effective scenario of the four we modeled is the combination of lane widening and congestion pricing. Oh, but we have a disclaimer, however, that lane widening may entail high costs for right-of-way acquisition, construction, and operation. It may also induce additional traffic that will further congest the road network as time goes by. Also, even if the LOS of the entire network is within the acceptable range, there are some links that experience congestion, long queues, and extended travel times. So, as discussed in the class, we can explore also traffic redistribution methods. And lastly, other measures may be considered, such as a proposal of a different interchange configuration, encouraging the shift to public transport and other traffic management policies. So that's it for our report. Any
Yes. So this is excellent. Yeah. Thank you. Is there any comment or question from other groups? Go ahead, please. Anyone? I have a few comments. Is it okay? First, the term traffic control, which you said as a traffic signal. So probably you better say it as a traffic signal because marking on itself is already traffic control, including the sign, right? So that's a minor comment. Second, can you compare actually you have the OD, right? So maybe you can compare with capacity restraint. I mean, instead of just using ideal flow, you can also use ideal flow and capacity restraint, which is already in IFN transport. And then third is the most crucial part here. I want to know what is the invariance in your model? Is it the flow, the OD flow is invariant, or is it the total flow in the network that is invariant?
the real world flow? I see. Sir, we did not change
The real world is the
invariance.
invariant. Okay, so the real world does not change.
Yes, Prof. Except for
Okay,
the reduction. The
except
reduction.
for the reduction. So what will happen if you set the total flow in the network as your invariance? I mean, the same scenario that you already saved, right? And then the one that you change is the base scenario you calculate using the OD, right? And then you get the total flow, okay? And then you record that total flow. Now, for the alternative scenario 1, 2, 3, and so on, you keep the same total flow instead of uh, real world data. What will happen? Because when you use the real world data to calibrate, right, you will get the internal state, which is the total flow. Once you create the alternative scenario, then you use the same real world data. I think that may have some problem there because the alternative scenario will have different configuration compared to the base scenario, right?
Easy. Yes. The
Right.
total
So in that case, when you use real world data, may have some problem. Depends on the situation, of course. But when you use just internal value like total flow in the network, that means the total demand does not change, right? So that's the assumption. So the total demand does not change. Then let's see what happens if the total demand does not change, and then now you change the configuration of the network.
Okay, Prof.
Okay, probably you will get better result. I don't know.
Okay.
Okay.
Because the total flow for the network was varying.
Correct. So in that,
network.
when the total flow of the network varies, then it's difficult to compare, right?
Okay.
I mean, you need to when you want to compare, you need to have certain things that is invariant.
Yes.
Does not change, right? So that's what my question about. So what is the things that does not change?
Okay.
Okay, good. Overall, your paper and the presentation is excellent. Okay, so please continue to rewrite your paper to be publishable. Okay, and send to journal or conference. I believe this is very nice result. Yeah.
Thank you, Prof.
Thank you. Okay, so who's next? Who will present next? Yeah, sure, Jerome.
Okay, I will present next, sir.
Okay, wait. Jerome. So I make you co-host. You can present.
Can you see my screen?
Sure, yeah.
Okay. Hi everyone. So I will be presenting a report on the analysis of the traffic congestion in Calayan Avenue Lawton Bridge using ideal flow network and JS. So it's a bit similar to the previous group, with some varying configurations. Like, right. First, we're gonna brief you with the area of interest. So it's the Bonifacio Global City Ortigas Center Link Road project. So it was done, like, started last 2017 in the 8th Avenue BDC, and I think it opened last year. Like it got completed last year. The area around Calayan Avenue was opened last year for uh road traversal. So this is a Google Maps representation of the areas, just to give you an overview. So it's this area right here. I think this is in Taguig and then bordering towards Makati. And another Google Streets overview of the area from Calayan Avenue. So you can see the flyover up there, and then traffic congestion is mostly happening in the intersection below it. So a bit of background on the area. Kalayaan Avenue Lawton Bridge. It is part of the BGC Ortigas Centerlink project, which was aimed at reducing the travel time between BGC and Ortigas Center to 12 minutes, from like projected before to have 30 minutes to 1 hour. So quite a big ask for this project to reduce the travel time to a mere 12 minutes. And generally, this is part of a bigger project of the government. It is part of the EDSA, the congestion program, which they aim to bring back EDSA to around 288,000 cars per day. So they plan to decongest it by introducing other areas for road traversal instead of EDSA. So this area is relatively busy area during rush hours, and traffic has worsened after the construction of the BTC Ortigas Bridge or link. The main problem with this is that it introduces traffic congestion to relatively narrow streets, especially on the Ortigas side. So the methodology of this project is to simulate using a transport model, the flow in the area, to be able to address congestion or traffic and provide alternatives. The main method that was used was the IFN transport model using real-world data derived from OpenStreetMap, and through the use of GIS, the OpenStreetMap data was manipulated to be able to input the data into the IFN transport model. So this is the conceptual framework. First, we gathered data using OpenStreetMap, and then using GIS analysis, we input the OSM road data and we identified nodes of interest for the node matrix. After that, we developed a road network in GIS to be able to input it into IFN. And then for the IFN model, we input the road network data and node data from GIS that we got from OpenStreetMap. We developed parameters for maximum congestion level. After that, it's the creation and assessment of base scenario. After getting values for the base scenario, we worked on formulating the alternative scenario, and then comparison and assessment of base and alternative scenarios, and finally conclusion and recommendations. So in here on the left side, we downloaded data directly from OpenStreetMap and in QGIS using Quick OSM. This includes the road network and the nodes in the area. And then nodes are not then manually mapped through QGIS to add to the node matrix. Okay, nodes were then exported as GeoJSON files from QGIS, which includes the node name and then the X and Y coordinates. And then it's then we input the GeoJSON file into a GIS data converter seen on the left side. It's able to convert the GeoJSON file into the node matrix that can be directly put into use into the IFN transport model. All right, for the assumptions on the link matrix, we use the data imputation settings in IFN so that we can estimate the link capacity, the max speed, and the road width for every single link. So for the results, here's on the left side, we can see the base scenario. So this will be the guidelines that we use for the alternative scenario. Since the IFN transport model requires a strongly connected model in order to function, a cloud node was added in order to connect all outstanding nodes on the edges of the model. As seen on the left side, the green links are representative of links connected to the cloud node. All right, for the constraints, we use the maximum congestion level setting used, and then the maximum congestion was set at 0.9. And then the capacity is set at 1 PCU per hour. So here's the final look of the base scenario. So there are several red flags here, including the flyover road link and the data. The road below the flyover, the Kalayaan intersection is also quite congested. So here's the base scenario performances. As you can see on the congestion level percentage, the maximum congestion was set at 90%, and there's an average of 47% in congestion for the entire network. And then the network speed is set at 55.61 kilometers per hour. Total flow is also at 131,811.68. So I was able to come up with one alternative scenario. So as you can see on the left side, this is the alternative scenario. What I did was I added the U-turn slot at the 8th Avenue corner 38th Street on the bottom of the model, added extra lanes for Fairlane Street on the Ortigas side and Lawton Bridge, and then transferred the U-turn slots in Kalayaan Avenue on both sides further away from the intersection. So I had to change the length of the links, and then added Brixton and Pioneer Street to balance out Fairlane on the upper side of the model. And here's the output for the alternative scenario. So the total flow is set at what the previous base scenario was, the sum of that. So it's going to be 131,811.68. And running through the model, we found that the alternate scenario has a maximum congestion of only 78.45% as opposed to the previous 90% from the base scenario. And then the congestion level before in the base scenario is at 47%, and then the average this time is 35%, also a 12% reduction from the base scenario. And the network speed is at 56.23 kilometers per hour, which is slightly better than the base scenario. So here are the comparisons of the previous model. So I added Fairlane and Brixton, not Fairlane, Pioneer and Brixton streets on the upper portion of the model in order to decongest the area on the flyover. There's still a lot of red nodes on the right side, as you can see, but those red nodes are representative of a 78% congestion, as opposed to on the left model, the red links, represent 90% congestion. So here's a output comparison. So total flow is set to base at 131,811.68, but the congestion level is significantly lower for the alternative scenario. But there's also a significant difference in the number of links on each data, since I added more streets and links into the alternate scenario. Conclusion and recommendation was found through the base scenario that there are definitely areas of interest that could cause congestion in real life. Using the alternative scenario, improvements have definitely been seen based on simulation. There's lesser traffic congestion, safer pedestrian routes, and wider lanes for easier access to Lawton Bridge. And recommendations to gain access to the OD matrix in order to identify more areas of congestion at different times. Another possible consideration is to use modal split analysis and explore which different types of transport methods are allowed or used in the area. That's it, sir.
Yeah, thank you.
Thank you. Thank you.
Is there any comment, question from other groups? So what was your invariance?
The invariance was the total flow of the network.
Okay. So it is interesting if you can tell your story, how you formulate the alternative scenario. It's basically a loop, right, to find the improvement.
Yeah. Okay.
So rather than just directly going into the final result, probably you can tell the story. How did you get this alternative scenario?
Oh, okay. Do I tell them right now?
It's okay. You can briefly tell so that the
Okay.
others also. Yeah.
First, I added a U-turn slot at the 8th Avenue. So on the bottom of the model, it's like you can't U-turn here from the bottom of here. You have to go to the 38th Street to go back to the bridge. So I added a U-turn slot there. I don't know if that's like legally impossible, but I added that. And then for the area with the orange street, so I transfer that. like in the base model, it's usually closer to the intersection, the U-turn slots. But in the alternative scenario, I moved it further away into Kalayaan Avenue. So the links got they're no longer suppressed or compressed. And then for after doing that, I found more congestion on the upper area. So uh, I had to do a lot of uh, manipulation into the base scenario. So that's why there's a lot of links and nodes added here. I had to make sure that all of the links, you can go back and forth in them since that's the real world representation. So what I did was I added an extra lane in Fairlane Street, which is directly connected to Lawton Bridge. And I also added an extra lane in Lawton Bridge to kind of smooth out the transition from Fairlane to Lawton Bridge. I guess that's it for the alternates that alterations that I did on the base scenario to be able to get
Right.
this maximum of 78%.
Right. So I think you can also improve the paper with that story so that
Okay.
the other people, when you publish it, they will know that this is not the magic that they can get alternative scenario directly. It's
Yeah,
actually a complicated
yeah, you have to alter
iterative, no?
a lot of data once you do a little alterations in
Right.
an area.
I think that is a very nice. Yeah. Okay. Thank you. Is there anyone want to make any recommendation or suggestion to Jerome? Yeah. So excellent. Thank you.
Thank you,
Please
sir.
reconcile with your group mate,
Okay.
if possible. Okay. Okay. So uh, next, who will present?
Maybe we can present, sir.
Sure. Okay. Please.
The screen sharing is still disabled, sir.
Oh, sorry. Screen sharing co-host. Okay. Andrea also?
Okay. Can
Yeah. Yep.
yeah, okay. Can you see our
Yes. Yes. I can see your slide.
so our paper is understanding the effects of the introduction of protected bike lanes in Makati Central Business District using ideal flow network and um modal split. So basically, the background of of our paper is that bicycles tend to become the main means of transport in many cities of the world, and basically we derive a lot of benefits. It has been established. Review of literature showed that bicycle use and the city's environment benefit from bicycle use in terms of it being eco-friendly and then reducing harmful emissions and what is more important is that it can reduce the number of cars on the street. In the Philippines, we mentioned this previously that there are 1 in 3 households that own a bike in Metro Manila. And as of 2021, 33 fatal accidents have been reported with 2,397 cyclist accidents. And in Metro Manila alone, there are 430 kilometers of bike lanes. Um, in our study area, it is the Makati Business District bounded by Osmeña Highway and Hill Puyat, which will be explained in detail by Andre later on. And it attracts thousands of trips across Metro Manila. and there is a presence of one Ayala terminal that serves as a transportation hub. And then there are public transportation routes along three main roadways bounding the area. We did a literature review, and basically, there is most literature highly recommends implementing bicycle facilities towards city development. What is more important is that one study in Metro Manila on the economics of the implementation of bike lanes, they did a review on bicycle policy, and their results show that implementing bike lanes resulted in reduced crash risk, improved cardiovascular health, it decongested traffic, created less carbon footprint, and increased tourism and employment. And then the implementation of policies and facilities is predicted to resolve heavy traffic, air pollution, citizen cardiovascular problems, and vehicular accidents in Metro Manila, as well as reduce expenditure on both individual and city levels. And they recommended that more policies are needed that will cater to both cyclists and motorists to achieve efficient citywide cycling transport system. So, and then other studies show that any transport policy should be simulated first and its impacts assessed with proper decision support systems, because only mutually agreed solutions are sustainable. And then it also helps disrupt societal, environmental, and economic well-being. And then the most important review of literature we did is also in the ideal flow network, which will be discussed by Andre in the methodology. So this is the bike lane infrastructure in the Makati CBD. This is our area. And then cycling is a main form of transportation for workers in the district. And then as SWS survey said that there are more bicycle owners than car owners nationwide, resulting in a ratio of bike to car owners of 4:1. And then other data include about 75% of cyclists bike to work. And in Ayala Boulevard, there is a presence of well-maintained bike lanes. And however, the issue with this is that um, a lot. Sorry, this is our study area with the nodes already in place. And then the aim of this study is to simulate the effect of the presence of protected bike lanes on traffic flow in the area, um, with the objective in mind that the results of the simulation will help policymakers and stakeholders in the area to have a clear picture of the effect of bike lanes in the area, and will lead to a more stable perspective and attitude to policy on bike lanes. This is because if you make a review of the news articles on bike lanes in Makati CBD, you will find that in spite of the presence and of the bike lanes, the policymakers and the residents have a push-pull attitude towards it. So there have been times that they would introduce bike sharing or remove the bike lanes, and it has always been met with protests. So this study is significant because if we simulate traffic flow with the presence of the bike lanes in the study, are shown to help or hinder the traffic uh, in the area, and if bike lanes are proven to be a possible positive change in the area. As a result, it would help entice and move more people to cycle instead of using private cars in the area, leading to health and environmental benefits, and promote multimodal use and lead people to use public transport in lieu of private vehicles. All of this with the hopes of that it will ease the traffic congestion in the area. So this is our basic framework. We look at the street network, ideal flow network, and modal split, the traffic flow, and then our conclusions. So And I will turn you over now to the transport expert in our group, Andre.
Hello.
Yeah.
So first of all, I'm not a traffic expert. Sure. Pero I did my best to do an analysis of our study. So for our analysis, we used two analysis models, the IFN model and model split analysis. For the IFN, we used base scenario of the CBD without protected bike lanes and another alternative with protected bike lanes. And another, we also tried to do a model split analysis with 5 models with different model splits. If Gracie could go back to the map, to the other map.
Okay.
Yeah. So in this for the study area, initially we wanted to use the whole CBD area as in the EDSA and the bound by EDSA and Osmeña. However, the group opted to use this particular area since uh, most of the since this area is the main activity center of the CBD and if and it is bounded by residential areas with Urdaneta village to the east, Magallanes village on the southwest, and the residential area of Barangay San Antonio to the west. So this is the road network that we have used. So all roads that lie inside this this shape, the bounds of this shape were used for the IFN study. So go back to this. Can you go back to yours?
This one. Okay.
So yeah, so to generate the road network, we use we use the OpenStreetMap data processor to manually derive road network using the website uh ideal flow. I forgot to put the link, but it's the website that we used for that. So to generate the road network, we use the following the bounding box, which is the bounds of the CBD area we wanted, and we only use the roads of the tertiary level as these are the roads that can accommodate heavy traffic flow. So next. Okay, so using the that geographic bounds, we got this map. And using the above parameters, we were able to generate a road network comprising of a whopping 966 individual nodes and 1,446 total number of links. So it can be noted from here that not all roads inside the CBD were detected by the IFN by the website. And for us, we decided to still continue using it. As we noticed that it did not include the small service roads that connected the inner parts of the CBD, which is okay since we just wanted to use tertiary roads. However, one road that we particularly wanted to include was the road connecting EDSA and the downbound. So you can see in the map there's a parang line, there's like a line. It should be connected to the eastward to the node. But unfortunately the website wasn't able to use it, and we ourselves were not able to manually put the nodes necessary to connect to. So despite this, we still just decided to use the map generated by the website. So okay, so as can be expected, how having 900 plus nodes, setting up the network required lots of automation, and hence so we did not actually bother to check all the points, all the nodes, since it would take lots of time to manually check all the nodes. So we just glanced at it and we just zoomed at the map overall and found that there are nodes. So like, okay, I guess, and we used it since uh, we we did not bother making any edits as to potentially derail the entire modeling. So yeah, setting it up, we needed the node ID, X coordinate, Y coordinate, and the ideal flow for the linkages. This is where we had to do some editing since uh, it consisted of link capacity, link distance, and back speed. So for the link distance, it was manually computed by by the website. And as for the link capacity, we checked. We did some checking actually. So it was not fully automatic. We did some checking of to confirm somewhat the capacities of the road networks, and what we found was the website used a standard of 1,500 link capacity per lane, and found that the minimum road size for uh minimum road size for the node metric was 2 lanes. So the minimum number of link capacity was 3,000 for a 2-lane road. And maximum of 9,000 for 4-lane road segments, particularly in the Gilpuyat Avenue and the Ayala Avenue, which are the two main roads in the area. So the website used 65 kilometers as a maximum speed, whereas the speed limit by the data by local government offices are 60. Which decided to just let the 65 kilometers. We did not find a way to manually change the 60 the individually. So for the ideal flow letters, so the what to set up the alternate scenario, because since we will be doing 2 scenarios, the first is the base, which was already preloaded, and that was and and we had to do some adjustments towards the on the whole on the link matrix. So in the Philippines, a single lane of road is usually 3 meters in width, and this would mean that a 2-lane road is on average 6 meters wide. 3 lane roads to be 7.5 meters, and so on. So basically, for every lane, you add up 1.5 meters. You add oh no, this is wrong. 3-lane road should be 9 meters. So basically, you add 3 meters per lane. So and according to the DPWH and DOTR, a standard bike lane should have a width of 2.44 meters. So to get the adjusted link capacity of each lane, we use the formula. Link capacity of a bike lane equals the link capacity times the number of lanes minus the bike lane width over lane. So it may seem medyo somewhat complicated, but it's just as simple as we just multiplied 2.44 meters with the 3 meter with the standard width of a line to 3 meters, and we got a ratio of that, and we multiplied that ratio towards the to the multiply that ratio towards the link capacity per lane of 1,500. From then, we got 1,200, and we just reduced 1,200 link capacity to all the nodes in the for the link nodes. So the results yielded. So we using the maximum congestion level as the IFN constraint. So initially we tried to use the real world flow, but as I emailed sir asking why it wouldn't work, and I found that the real world flow froze my was freezing the browser and was not able to yield results, probably because of too many nodes and languages. So we wanted to compare the real world flow and the maximum congestion levels, so just to see if there are differences in these two. But ultimately, we just ended up using the maximum congested level since we were not, since I don't know if it's because of the laptop or it simply cannot load all the data, but the real world flow causes the laptop to freeze. So as we ended up with maximum congestion flow. So from the IFN results, we could see the total flow to be 745,000. When you go back to the slide. Okay, so these are the results. We had a congestion of 15%, which is admittedly too low to what we were expecting. Since we used the maximum congestion level, probably owing to the fact that there were a lot of points, there were a lot of nodes in the, but we did find some nodes that were above 50% in congestion, which we pointed out, and one node in particular had a maximum of 90 congestion flow, which was uncharacteristic since the average was 15%. Okay, so next. So the results of the base scenario, so the over data had low congestion levels, but upon further analysis that there were 5 linkages on which congestion levels were recorded to be above 50%. So of the 5 of those 4 linkages, they were found to be in near proximity to the other. So if you can see in the image, there's an arrow. I don't know if you can see the green arrow. It points to a particular piece of part of the road that had 4 of the 5 linkages which had about 50% congestion, and these linkages had 57.86% to 90% congestion levels on that single part lang. So of all the 1,000 for of all the 1,000 plus na linkages, there's only 5 had about 50%, and 4 of those were in that particular area. And upon using Google Maps, found that area to be a particularly tricky part of the road. So it is a more solo street. It's a two-way road. So, but it it has an access point to that has a one-way road. So I think the IFN network sees this as a particularly difficult thing to process since there's too many road linkages, and it had to use all these nodes for the project. So that's why we think it's the congestion was that way. For the next, so for the next, we use an alternative scenario. So for the second model, we used where we used the lower link capacity. This is what we got. So total flow was at 44,000, which was 447,000. And congestion levels actually went down 12.6.468, and maximum congestion levels was 90. So of 4 linkages, the 4 linkages we found earlier, they were the only 4. They remain to be the only 4 about 50% for this scenario. And although this linkages also, and additionally, this linkages also had the same congestion values despite having lower capacity. So I don't know how that may have been, but it basically registered the same congestion values for those 4 nodes in shown previously. Okay, so next. So when we compared the 2 scenarios, it can be observed that from the base scenario, the total flow decreased by 40% in the alternative scenario. So this is expected. We expected this since it is a direct consequence of decreasing the link capacity of the road network. So since we lessen the link capacity of the roads, we ended up with lower total flow than when we had all lanes to be usable. So next.
Yeah.
Sure. So for the comparison of the network averages, again, average flow also decreased by 40%, which is again, since the capacity of the road network lessened. However, despite the overall decrease in flow, congestions level lessened by 2.56% from 15.22% to 12.6%. And with the travel network travel time, networks with a network delay remaining virtually the same. So next, despite having lower flow overall, congestion went really better, and travel time wasn't really affected that much. So to discuss, we so based on the results of the models, the establishment of a protected bike lane system along the Makati CBD, which reduces the effective road width of the road system, would result in an over decrease in vehicular flow in the area. And such a change would cause less vehicles to be able to move around the area. However, despite this, the IFM model has projected that congestion level would decrease so long as total flow decreases. So the addition of a protected bike lane network while decreasing the flow can, however, still be a positive change in the area, as it can encourage active mobility, therefore lessening the use of cars in the district and overall reducing the flow. So this is our findings for the initial findings for the IFN. So for the next, we used a modal split analysis. Initially, what we wanted to do was connect two studies, but upon doing it, we were unable to actually connect the two processes. So it was kind of we were unable to find resources which these two was able to connect. We initially wanted to do a model split, but despite not being connected, we just wanted to analyze it further so as to see another to use an since for us to use another analysis method for the study. So for the model split, we used Ayala Avenue and Gulpuyat Avenue as the road linkages to be studied. These roads contain the bulk of vehicular traffic in the study area and are used as the main thoroughfares when traveling inside the central business district. So for the link capacity and link capacity, we used the same one from the IFN model of 1,500 pieces per lane. And for the link length, the measurements were made using Google Maps for 2 road segments to be used. And for Ayala Avenue, it was found to be 1.91 kilometers, and for Bendia, 1.78 kilometers. Okay, so next, so you can see this length. Okay, so next. So for trips demanded, so the Philippine Statistical Authority census of 2020, Makati City's nighttime population in 2020 was 629,616. So nighttime population meaning the population that reside in the households. However, in a 2012 study conducted by the Makati Transportation Study, it is projected that the maximum daytime population of Makati City, which is whopping for 4 million plus people, or about 7 times of its current population, to which the Makati CBD plays a huge role. So we initially wanted a more up-to-date number, but unfortunately, also we were unable to find a figure that was close, a figure for 2020 or any, and 2012 being the latest one we could find. So from these values, the group calculated the trip demand for the Makati CBD by using the formula. So trip demand equals daytime population minus nighttime population. So it's simply we just wanted to know how many how many people were not residing in Makati City households but were working in Makati. So for the trips demanded, this produces a total trip demand of 3,600,000. But for the model split analysis to work, we needed an hourly trip demand, to which we divided it by 8, using 8 different time windows of hourly time windows. So 4 p.m. to 5 p.m., 5 p.m. to 6 p.m., 6 p.m. to 7 p.m., and up to 12 midnight. So it was 8. So which equals to for 151,437 demand per hour for all trips. So it's a lot. And the demand encompasses all trips made by the CBD using all modes of transportation. However, for this study, we only plan to analyze 3 modes in analyzing demand: private cars, buses, and jeepneys.
Oh.
Okay, so Asinas et al. They conducted a study on the transportation preferences of office workers in Makati and found that 72% use public transportation and around 27% use private vehicles, which are either owned or rented as or rented or which is TNVs. So the total number of workers surveyed, around 13% of them use buses and 24% use jeepneys. So we initially wanted to use more hard data from the Makati City or Makati Ayala. However, there was not we were not able to find a percent data on how many people on the modal split
Right.
of people in Makati City. So we decided to use a literature that's seek to study this and that was the data we used. For the study, we only used the private cars, buses, and jeeps, totaling around 64% of the sample size of the initial. So by multiplying this value, the 60% we multiplied it by the hourly demand, since this is the one we wanted to analyze, the private cars, buses, and jeeps. We got 306,987. So next. Okay, so distribute the hourly demand along the two road segments that we used. And we used the TFRB data of public vehicle routes that lie along these roads. So these are we checked out TFRB to get the bus data, the bus routes running across these road segments, and this is what we got. So of the 15 bus routes that lie along the study area, 15 of them pass through Vilpuyat, while 9 of them pass through Ayala Avenue. For the jeepney routes, of the 6, 3 of them pass through Vilpuyat and 4 of them pass through Ayala Avenue. So what we can gather is, so when we combine the data, we can gather that this 6 jeepney routes are responsible for the 64 around 24% of the total demand as per the Asinas et al. Study, which we used, used. So next, so trips demanded. Yeah, using the said data, the group found that okay. So so for the hourly trip rate percentage, we used so basically we used the total number of PUV plus PUJ over the total that flight along Gilpuyat divided by the total number of PUVs and PUJs, and found that 58% of the PUV and PUJs travel along Gilpuyat, while 42% use Ayala Avenue. So this is how we will be splitting the trips demanded, since if with the rationale being since with Ayala Avenue having more route, Hilpuyat having more vehicles flying along its route, that means more people tend to use that route as opposed to Ayala Avenue. So yeah, so next. So we also needed to know the passenger car units and car occupancy. So Espinilla et al. In 2010 was able to derive local PCVU values for vehicles along 4-lane highways. So in this study, we will be basing our PC values for private vehicles, public buses, and for public jeepneys on their study. Last for bikes, the group used transport for London suggested value of 0.2 PCU. Next. So for car occupancy, on the other hand, is also needed. So this study assumes that movement occurs at the end of the day and where people were going home, and hence maximum capacity for buses and jeepneys were used, and for private vehicles, passenger occupancy would be one per private vehicle, assuming that only one person was inside the private vehicle at the time when going home. So the average city
Andre,
was
is it possible to focus on your bike lanes?
yeah, sir. We tried to focus on the bike lane, but it was we found it hard to use the modal split on the bike lanes, and
Okay.
plus, because of the values we got. So if you can skip to the fourth the to slide 39.
Yeah.
Okay,
It seems you have two separate studies that is not
it
connected.
actually turned out that way, sir. But we wanted to use to study bikes. However, upon using bikes, it was actually hard since public transportation was also used in the along the main lanes.
I
We
see.
actually, sir, we wanted to make the model split analysis and focus on the IFN, but I don't know, we spent much time on it, so we just wanted to show the results, even though we it wasn't actually that useful to us. But we
Okay.
could have
So
just ended with
maybe
the
maybe
IFN.
we can discuss maybe we can discuss it later separately. Is that okay? In that case,
We
yeah.
wanted,
I think
sir, we actually wanted to find a link between the two, but unfortunately we were not able to find a link. But since the
yeah.
data, since the computations we made was the effort we have put, we wanted to include it. So, but okay, but for now, let's just skip that part and maybe
Okay.
we can skip together. So we'll go to the conclusion.
Okay.
So for actually when we use the bike lane, so what the five graphs basically says is as car passenger was shifted towards bicycles, it actually leads to lesser congestion, uh, which was actually um, expected since one key element of the modal split analysis was this. We used this metric, the PCU and passenger capacity, and wherein a higher ratio correlates with a more efficient use of transport space for transportation. So using this metric, we get issued as follows. So a private car with a PCU of 1, a passenger capacity of 1, would have a ratio of 1, which is not very efficient. So for bikes, it was 0.2 over 5, which yields 0.2 over 10, which is 5. So it was more efficient. For jeepneys, it was 23 over 2.2, which was not efficient. And for buses, it was found to be the most efficient. So initially, we wanted to test for the bikes, but ultimately, we ended up with the conclusion that public transportation is actually the most
Okay.
efficient. Despite using people shifting to bikes was simply not enough to accommodate the total demand in the area. That was what we came up with. So
Okay.
that was the link to the study. So
Right.
so for the results, yeah. So uh, replacing the bike was not enough. So in this, the public transportation is really the key to solve the congestion when it came to modal split analysis. As for the
Okay.
next
Right. Right.
so conclusion, so based on the IFN results, it concluded that the establishment of a bike lane network at first could test the space of the rest of vehicles. However, in the long term, it could help ease traffic flow, especially as people start to use infrastructure. Despite being outside the bounds of the study, the group suggests the feasibility of having a bike sharing system inside the CBD to encourage the use of bikes, which could help ease congestion of the whole traffic area. As for modal split, despite bicycles being more efficient in terms of space, public transportation remains to be the best solution for easing the congestion in the area, and with cycling acting a more complementary roles in the solution. So next. As for our scopes and limitations, so throughout the study, data sets proved hard to obtain, especially the hard data which we wanted to use in the Makati CBD area. So the same could be said for related literature pertaining to worker populations and transportation, as we are only able to find one study, the study quoted earlier, and although the number. So to be better, have been better to get more sources direct from the source, which for the values. And data used in the study were loose estimates, and actually they were not loose estimates, but from the studies, however, they were not backed by any actual hard data or
Right.
that. Yeah, so the group suggests to obtain actual hard data from concerned private and public offices. And last, scope, problem scope. One thing we found hard for the study was the actual size of our study area. So if if we were to do this the study to rerun the study, we would have probably limited the study area to a more compact, so as to properly get it was too.
Okay. Okay.
So that's
So is there any comments, suggestion, critics probably from other group to Grace and Andre? Go ahead. Yes, Katrina.
Sir, I think, Prof, similar to what you have said, maybe they can focus to just changing the parameters for the bicycles, because I think the focus might have went to
Hmm.
the other modes instead.
Yeah.
But the conclusion is, I understand the conclusion well in relation to the bicycles.
Hmm. Right.
Actually, sir, yeah, but we included the other modes of of just to see in the scenario, like we have 5 scenarios there, and the fourth
I
one was in all
understand. So
shifted vehicles, because we also needed to look into it, because we could not really just isolate the bicycles, because the problem in the area is um there are stakeholders who want to remove the bicycle, want to change it to shared lanes. So in a way, as a general overview of the whole
hmm.
situation and simulation, we find
Hmm.
that it is helpful, and then it did show in our results that public transportation is still the best, while we push for the cycling. It's still
Okay.
efficient in the area.
So yeah, okay. Before I give, so is there any other comment? Other groups probably. Okay. So there are several problems in your models. Okay. Number one is your invariance. Okay. This is for all. So when you create the model, say using IFN, okay, your base model can be from any data or for assumption, for example, maximum congestion 0.9, like what this group was making, right? But when you do alternative scenario, you should stick in the maximum, in the total flow in the network. When you create this, your problem is you create the alternative scenario with also 0.9 maximum congestion. Then you cannot compare because that means different time, right? Totally different time scale, not at the same time. When you want to do at the same time, that means the total demand should be the same, right? If you create the base scenario 0.9 and then alternative scenario also 0.9, when that happen, we don't know. So you need to have another model to tell the timeline. So in this case, you use the same timeline, but both are using 0.9, the meaning is rather confusing in this case. So it's better if you use alternative scenario with the total flow in the network the same. That means the total demand does not change. Okay. Then you can compare, right? So this is number
Sir,
one comment.
how are we to maintain the maximum flow as the same?
Correct. The invariance should be total flow in the network, right? But when you set the total, your invariant is 0.9 maximum congestion. That means you have different timeline because the alternate scenario is actually different network structure, isn't it? Then when that happened, we don't know. So this is difficult to compare, right? Because you are running parallel two different lines with the same maximum congestion, which is 0.9. This is a problematic in making the assumption. Okay. Remember, in any model, the most important is what is the invariant, what is the assumption behind. Okay. So if you make mistake in that, so it is a trouble. Okay. And second comment. Okay. Second comment is about you are using modal split, but not include the bike, right? Which supposed to be, if your focus is actually on modal split of the bike, then let's include focus on the bike only. But your modal split is deviate away to go to public transport. So probably you need to rewrite so that if your focus is actually public transport, let's do rewriting about public transport rather than the bike. So in that case, your objective, your problems must be different, right?
Sir,
So
the scenarios, we have 5 scenarios in the modal split. One of the
mhm,
scenarios is actually if all were to use bicycles. So that was the part that
right.
Andre's skipped explaining. We have 5 scenarios for the modal split,
I
actually.
see,
So
I see.
it's that's the part that he was asked to, but
Skip. Okay, sorry. Because it was confusing when you
uh,
started to
no,
deal with
yeah.
out of
Sir,
focus, right?
There
we
were
just
five
wanted to
scenarios, sir. So the scenarios was showing different types because there are different vehicles in the area. And then the slide that Andre said to show the fourth scenario was actually the bicycle scenario. Like if all were to
Okay, you
use
want to show that now?
maybe Andre can show it again, sir. Use na lang your slide, Ray. So you have more
Only
focus.
that part. Okay, yeah.
The modal split 1 to 5 scenarios.
wait, I'm opening the file.
You can
So
show
yeah, for
model
this,
1, Ray, briefly, for you focus on the so the sir can see the different scenarios we have.
so sir, at first we used bike uh, for cars. We used private cars just to establish a baseline. Using the model split, we did it 150 minutes. Yeah, so that was the bonus. So for the skip to the four. So instead of cars, for the second we actually used the actual. So for the actual share, so this was what we got. So for the fourth, did, uh, we changed the cars to bikes. 15 years. So overall, it was found that the number of lanes needed would be 18 with 14 for L, which was still overwhelming, such given the current condition of the road. So, and for the last, that's when we decided, we realized that why don't we check na how it would be if you would use public transportation. So that was it was that was what we. So from there, we got a conclusion that the public transportation is
Okay.
actually. But we could have
So-
stopped here, sir, but the bike
Right.
lane, but we wanted also to show public transportation.
Okay. So you mentioned earlier that actually public transportation is better alternative than the bike lane. Is that correct?
Yes, yes, sir.
So, but
Boost.
I did not see that in your conclusion that you write.
Sir, it was in this. So
Yeah, in here you did not say that.
As for the modest state results, it was found but public patient to be the best solution for this
Okay.
Beside the acting among complementary.
I see. Okay. So the public transportation is the best. Maybe the wording need to emphasize because
Yeah, sir.
it seems like you emphasize the bike lane, but actually the best public transport.
And actually, sir, our scenario 2 is a mix of bicycles and transport cars in the area. It was not 100% cars. So we just
Right.
look at
So
the
probably the way you write only is the problem. Okay, analysis is fine, but only the way you write can emphasize
Yes, sir.
on different matter. Yeah.
I realized, sir, the way the methodology was set up was actually
Yes.
getting into the.
So if you want, you can revise up to next week before the final exam. Okay. Yeah. Thank you.
Sir, I will.
Yes.
Can I schedule sir,
Yeah. Okay.
consultation regarding the
Sure.
Sir.
Yes. Okay. So who's next? Jofi?
Yes, sir.
Okay. I will put you as co-host.
Sir, can you make Miss Magpili as co-host instead?
Who?
Miss Magpili. Nina Magpili.
Sir, I will
Nini.
be the
Okay.
one sharing the screen.
Yeah. Wait. Where is Nini? Okay. Go. I haven't seen your paper in Moodle.
We have not yet submitted, sir, the paper.
Okay, so please submit.
Maybe later, sir, we can
Okay.
submit. We are just fine with it. Okay.
Okay.
Good evening, classmates and Sir Ricardi. So I and my group mates will be Sophia and Jovi will be presenting the scenario analysis of increasing the bus capacity and the number of dedicated bus lanes in EDSA. So for the brief breakdown of our presentation, we have the background, the objectives of the study, methodology, the results using the IFN transport and headway analysis, our conclusion, and some of our references. So EDSA, as we all know, is the major connector between the northern and southern part of metropolitan area, as well as the south and north Luzon in general. It runs around 24 kilometers from Caloocan in the northern part of metropolitan to Pasay in the south and is known for its heavy traffic due to volume of establishments in the area. So for the current EDSA traffic situation, based on the latest report from MMDA, the average daily traffic generated in EDSA already reached around 410,000 vehicles in 2022. The average speed during GCQ period is at 27.6 kph for northbound and 31.57 kph for southbound. And due to this traffic situation, there are various initiatives that have been implemented, such as EDSA Carousel. So EDSA Carousel is a bus rapid transit system in Metro Manila. So the interim operations began in June 1, 2020, and the full operations began later on July 1, 2020. So in our study, we consider just the major intersections along EDSA, which are Shaw intersection and the Ortigas intersection. So our study aims to investigate the effectiveness of increasing the capacity of the current bike lane by adding dedicated by bus lane and increasing the capacity of the bus unit along EDSA. So for the research question, how will these scenarios impact and reduce traffic congestion along EDSA? We have the specific objectives of this research is to assess the impact of expanded bus lane capacity on the traffic flow, congestion level, and travel time along EDSA. Assess the impact of introducing additional dedicated bus lane and assess compare these results to recommend the most desirable scenario for implementation along EDSA. So this is our research methodological framework. So for the input, we have the geocoded nodes and identified links. And then for the processing, we have the online IFN transport and then the development of alternative scenarios. For the output, we have the congestion level of base and alternative scenarios. For the second part of our analysis is the computation of headway. So we have the passenger demand and bus capacity as our input, and for our output, we have the comparison of different scenarios. So for the our methodology, the first part is the network modeling and development of matrices. So using the Google Map Street View, we are able to examine the traffic flow and set the different nodes of our network. So the different nodes were set based on the number of lanes, change in the number of lanes, the lane merging or diverging, and different intersections. The geocode location of the identified nodes were also determined using the Google Maps and were used in setting up the node matrix. So for our node matrix, we have the node ID, the X coordinate, and the Y coordinate. For the second part of the network modeling and development of matrix, we have the development of our link networks. So the assumed lane capacity was set to 1,800 PCU per hour as per the PWH standard. And then the network links are identified with the set of origin and by setting the origin and destination node based on the route of vehicles passing through EDSA. Separate network links were developed for the bus lane route, and then the number of lanes were determined using Google Maps Street View, and the length of links were identified using the measuring distance tool. The maximum speed allowed is at 60 kph, and these parameters were used in setting up our link matrix, which are link ID, origin node, destination node, lane capacity, length of link, maximum speed, and the number of lanes. The created node and link matrices will be used in the network analysis using online IFN transport. So this is the sample of our network link created. So the second part is using the online IFN transport. So first, after creating our node and network matrices, we will check if it is strongly connected. And then the parameters used in this model is the traffic assignment model was ideal flow network with the following parameters. The maximum congestion level for the base scenario was at 90%. BPR travel time model, lambda equals 0.5, and mu is equal to 0.4. The capacity to
1.5?
is 0.5.
0.5. 0.5, not 0.5.
Yes.
Okay.
And then the capacity to stochastic model is just a simple proportion. So after getting the results in our base scenario, the total flow will be used in determining the congestion level of our alternative scenarios. The first alternative scenario is increasing the number of bus lane from 1 lane per direction to 2 lanes per direction. And the second alternative scenario is increasing the capacity of bus unit using double-decker bus unit. So for the third part of our methodology is to check the operability using the computed headway. To assess the operability of each scenario, the headway between buses were computed based on the total demand. This was obtained from the published ridership of EDSA Carousel and the MMDA average annual daily traffic. The assumption for the bus occupancy, bus PCU peak or demand, and capacity were also set. And then for the last part of our methodology is the analysis and comparison. To assess the most feasible scenario, the congestion level and headway of bus units of the three scenarios were compared and analyzed. So for the results, this will be discussed by Jovi.
Thank you,
Jovi.
Miss Nina, for um, sharing to our class pertinent details regarding our study. So right now, let's proceed to the results of our network analysis using the online IFN transport tool by SIR. But first, let's look at the map on the right side. So that is the base scenario. So it's an overlaid network of links and nodes and overlaid to the map of our study area. So that is this section of EDSA from Shaw to Ortigas. So I hope you can bear with me with the poorly overlaid network of links and nodes, but that is there to visualize how we identified the nodes and links. So running um, the base scenario, given the parameters that Miss Nina has mentioned earlier. So we got these values for the total flow. So we have 1,300, 100,300, 1,039. What? I'm sorry.
150.
139,416 PCU per hour for the total flow, and other values for the network entropy and network entropy ratio and network max entropy. So the total flow was used as the invariant for the alternative scenarios to determine the congestion level and other statistics. Next slide, please. Yeah, so further information regarding the base scenario. So we have an average flow of 1,742 and an average congestion level of 32%. And from this, we found that there are congested links. So these links include links that connect node 30 to node 32. So that is the node located near the Shaw intersection going to the Bonnie node link, and that is the 90%. That was the link that has the 90% maximum congestion level, and node 34 to node 4, the U-turn to northbound link has a 78.65 congestion level, and node 17 to node 16, so that is the node from the Ortigas intersection to the node located to the direction of Cubao, and it has a 76.04% congestion level. Next slide, please. And for the alternative scenario, so we have considered adding another lane for the busway. So for that, other than adding another link or increasing the capacity of the link of the busways, we change the capacity of links that are affected due to the addition of another lane of busway. So yeah, with that, we got an average flow of 1,742.7 to 1, and an average congestion of 33.98. And the maximum congestion is found in the link that connects node 30 to 32. So that is the same link that is most congested in the base scenario. So that link has 93.7% congestion level, and the same link, the node 34 to node 4, also got the second highest congestion level, which is 84.02, and node 17 to node 16, the Ortigas to Cubao node link, also has a high congestion level at 79.77. Next slide, please. And lastly, the alternative scenario where we increase the bus capacity. So we just doubled the capacity of bus lanes, and so we can achieve this by having instead of the usual bus that we have here, we could run a double-decker bus instead on the busway. So that would essentially double the capacity of the busway. So with that, we changed the link capacity to 3,600 from 1,800 for the busway links. And with that change, we got an average of 1,742.7 flow, and congestion level, overall congestion level, the average of 32.38%, and the maximum congestion level, we have 89.69, and that is also located, and that can be found in the link that connects node 30 to 32, the Shaw intersection to Bonnie node link. And next link that is most congested for this scenario is the same the second most congested link for the first two scenarios. So that is the link that connects node 34 to node 4. That is the Shaw U-turn to northbound link with 84.02%, and node 17 to node 16 with a congestion level of 79.73. And next slide, please. So comparing the three scenarios, we can see that the max congestion level has increased for from the base scenario, which is 90%, to 93.6968, for the two-lane busway. And for the increased bus capacity scenario, we have 89.6902, which is approximately 0.3% less. And we can see that the average congestion level for the two-lane busway is the highest among the three scenarios, and the increased bus capacity average congestion level is lower for the increased bus capacity scenario compared to the base scenario, which is 32.74. And for the next part of our study, Ms. Sophia will discuss the headway analysis.
Thank you, Mr. Jovi. So this is just a quick check in terms of operation that we did for the headway of the buses. So based on 300,000 average daily ridership of the bus carousel, we computed the total demand per day and per direction. This was just divided by 2. And then the total demand per hour based on a peak hour demand factor of 10%. And then the total bus based on the PCU of bus occupancy of 52, and then the PCU based on a bus piece factor of 2. So we for the base scenario, we computed the dispatched headway of 12.48 seconds, which is less than the computed brick wall headway, which this is based on the length of the vehicle, the time to stop, based on the deceleration and the speed, and also the reaction time. But this is still considered very low, based on an average brick wall headway of 1.5 minutes per lane. And then next. So for the alternative scenario of additional lane, we assumed, since there will be additional lane, we assume that there will be a 40% shift from private vehicles to bus, considering the additional capacity. So we just assume 40% since based on the computed person trips on the based on the AEDT, there is already a 40% user of bus. So just additional 40%. We just like doubled that when we added the lane. So the computed headway and on this one is the almost close to the first one, which is 12.62 seconds per lane or 0.21 minutes per lane. And then for the next one, the increased capacity, we got the same results actually. But the difference on this one is just the bus occupancy from 52 to 104. So the result was the same since for the previous one, this was divided by 2 as well, since there will be 2 lanes already. So we also got less than 1 minute brick wall headway, computed headway. So in terms of headway, all the 3 scenarios are okay when we compare it with the minimum computed headway necessary, which is 10.55 seconds. This is the headway necessary for the bus not to hit each other. So next for the conclusion and recommendation. So based on the IF results of the IFM, the increased bus capacity scenario is the more desirable alternative scenario than the additional lane, since surprisingly the additional lane would even yield a higher congestion level than the base scenario, although the difference is very minimal only. So to address the traffic situation along EDSA and maybe for future studies, we can explore encouraging the use of alternative routes, strict implementation of vehicle volume reduction schemes, such as number coding, explore other means to discourage car ownership or other usage such as through taxes and additional registration fee and road pricing system. Car ownership regulations such as through vehicle quota system and instill encouragement of the use of rail and busway public transportation and other modes of transport such as active transportation. Also for our study, maybe for features recommendation to conduct a comprehensive cost-benefit analysis to assess the feasibility of the proposed interventions, use the OD matrices along the study area for more accurate comparison if available, and expand the study to include the whole stretch of EDSA. So that's it for our report. Thank you very much.
Very good. Yeah. Any comment, critics, question to this group from other group? Anyone? Okay, so can I just ask several questions? So did you include the cloud node or exclude the cloud node in your model? Do you include or exclude the cloud node? Because I notice your network speed is a little bit strange, like 200 kilometer per hour. There, your network speed is like 100 kilometer per hour, and then maximum is 200 kilometer per hour. So where did that come from? Why?
So we excluded the cloud node.
So maybe you need to exclude the computation of the cloud. Right. And then second question is about how do you get the double capacity of the bus? I mean, when you double the capacity of the bus, that means only the number of people per hour, right? That actually improve, not the PCU value, right?
Yes,
Is
sir.
that, did you convert it?
We just double the lane capacity, sir. So from 180 to
Oh,
1,600.
that's not correct, right? But because of the unit is not correct, isn't it? When you double the capacity of the bus, it's people per hour that uh, increase into the accommodation of the bus, but the number of lane does not change, no? So in that case, you need to convert back to PCU per hour first before you increase the capacity, right? Is that correct? The lane capacity you increase by 2. Well, that's equal to double your lane. Isn't that so?
Yes, sir. That seems like it, sir. We'll address that,
Okay.
sir.
Yeah, okay. So please consider it again. Thank you. In overall, I think it's very good. Okay, so
Thank you,
is
sir.
there any question to this group or shall we move to the next group?
Just a comment, sir. I
Okay.
think the result that Sophia mentioned shows what you were telling us about, that sometimes it's really not necessary to add lanes because their results showed that they have improved by just doubling the capacity of the bus. they actually improve the conditions. So what you were driving at, that most politicians or policymakers would always say add lanes, is actually not the solution all the time.
Yes, but what they compute, I'm still not sure. They need to justify the computation first. Okay. Sometimes we can reduce.
Arrive at the same.
Right. Okay. So go. Who's next?
Sir,
Resi. Okay.
rest is group, sir.
Okay. Go. I think you are already co-host. So
Ah, okay. I will, can I ask for my group mates? Are you ready? No. I will just share the screen.
okay.
Okay. Wait, sir. Are you able to see my screen now?
Yeah.
Yeah, okay. I will just sense full screen. Yeah, there you go. Marie?
Yes, hello. Good evening, everyone, and to our fellow classmates. So
Okay.
here's our group report. This our topic is about a comprehensive analysis and the proposal for the traffic management in Pilar Bataan. So our group mates is me, Marie Karunungan, and then Resin Nograles and Abby Viernes. So next, please. Slide, please.
Oh, sorry. You haven't sent your paper also?
Yes,
Yes,
sir.
sir. We're just gonna finalize it tonight
Okay.
once we have
Okay.
gathered your comments
Okay.
and
Okay.
recommendations. Thank you.
Go. Sorry.
Next slide, please. So next slide, please. So it's just a brief introduction of our study area, which is in Pilar Bataan. It is located in it's located in Central Luzon in the province of Bataan. And it's bounded by the municipality of Orion in the south, and then the city of Balanga in the north, municipality of Bagac in the west, and the Manila Bay in the east. Next slide, please. So the current road networks of Pilar, we have two secondary roads and two tertiary road, which is the Roman Expressway, then the Governor J.J. Lino Road, and then the Junction Layak Balanga Maribel Sport Road, which is had a total road length of 11 11,241 kilometers for the secondary roads. And then for the tertiary road is about 5,943 kilometers. So next slide, please. Next slide, please. So here's the map, the road network map of Pilar. On the traversing from the north to south are the Roman Expressway and the junction Layak Balanga Maribel Sport Road. And on the traversing from east to west is the J.J. Lino Road, which is the orange one. And then, okay, the red one was the Roman Expressway, and then the blue one was the junction Layak Balanga Maribel Sport Road. So, next slide, please.
For our study area, the group opted to choose the Pilar's Central Business District, which is connected to the to the mixed-use character of its neighboring city of Balanga. Next slide, please. So just a quick background because we've discussed it from our last meeting. So to give a quick background on Pilar CBD, it was purposely put there as it facilitates seamless effort in catering to any overflow of urban sprawl coming from Balanga, which is the center of Bataan province. That is from it is located on the north of Pilar, and then passing through Pilar going to Orion at the south area of the Bataan. Next slide, please. As discussed by Marie, the of the road networks, we'll just focus on Roman Expressway, Governor J.J. Lino Road, and the Bataan National Road, or the JCT Layak Balanga Marivela Sport Road, because the Super Roman Highway caters to big buses such as Bataan Transit and Genesis, serving passengers coming from towns of Bataan going to Manila, and then minibuses and vice versa. While for the PUJs, the jeepneys is flying from Balanga to Orion, the down area, the lower part from Pilar, and vice versa. And while the also the PUJs minibuses flying from Balanga to National Road and vice versa using the JJ Linao Road. Also the presence of the colorum tricycles, private vehicles also uses the National Road to cater passengers within the town point to point. Having that said, the CBD has attracted many public or private vehicles servicing on the area. Next slide, please. Um, gathering the data, we use RBIA, or the Road and Bridge Information Application Database from the DPWH. As seen on the screen, we focus on the area where experiences heavy traffic during the rush hour. In this database, we may be able to get the annual average daily traffic, the traffic survey sites, the number of lanes, road network, and VCR of the road networks. Next slide, please. Here are the traffic sites notes we considered in our study. And for the rest of our presentation, Resi will present the base and our alternate scenarios.
So for our base scenario, we have actually collected the AADT for 2017 to 2021, and then projected it to up to 2023 to get the current condition or the existing condition of the network up to 2023. So for our base scenario, we have collected, I will just show the Excel later, but we have uh, put everything in the slide, but I am actually comfortable presenting it later on the Excel file. So just to show you the flows we have determined, those are the flows. And then we have identified the link or the flow from using the traditional method of getting the congestion or the VCR computation. We have identified that link A to B reach 1.06 or more than its capacity. So it got an LOS of F, level F. And then the rest of the links have an LOS A and B. So this is that link. And then for our base scenario, we have actually used also the AFN transport network. So using a total flow of based on our actual AADT data that we have gathered. So our total flow is actually around 4,214 um, PCU per hour. And then getting the base scenario, we have identified that the maximum actually this result one of the I mean the problem that
Very
we
low.
have identified the last time we presented is our data set doesn't actually necessitate any intervention because of the low congestion level or
Hmm.
yeah. But for presentation purposes we actually did not change topic as recommended by user since uh, and we have already collected our data and processed it already. So we have stick to it and try just to show you how we will reduce the or how we will solve it or reduce the congestion level. So from here, the maximum congestion level only is around 9.96 or 9.9615. And then for the alternate scenario, what we did is we actually add lanes. Maybe I can just share the Excel file and just to show you. Here's my Excel file. Okay, I'll sh- I'll just show you again this one. Are you able to see my screen now?
Yeah.
Yeah. So from the actual AADT, using the also we have used the equal probability because we have processed this and then we did the point 0.5 for both directions for each node or for each traffic survey site. And then I have also computed this one using equal probability for A to left, A through, then label it as A to B, A to F. So it's a tedious process in processing this data. That's why we actually did not change the topic anymore. And then we have followed instead of the 8% factor that we are using in the DPWH, we have followed the recommendation of Sir to use 10% as it is the usual percentage for the peak hour factor to get our AADT here or the hourly. And then uh, there we got the LOS. I just highlighted the LOSF and the one with the LOSB. And we usually in our answer in our uh, method here in our department or division, once we have identified that it's nearing or reaching zero point 0.6. Yeah, zero point 0.6 is the one we're using where we could actually propose an intervention. It's either traffic signalization, something from small solutions until we got or until we get the intervention with the most benefits. So I actually highlighted this also. So these are the basis of our alternate scenarios. So for the alternate or for the first scenario is wait, I'll just change my share screen. I'll go to the other slide. I mean other Excel. Where is it? There you go. Okay. So for the scenarios, we just added another lane for different links. The links that I have highlighted earlier. So for this link, for the alternative one, we add one lane to from A to B. So you can see here on our base scenario that we have just doubled the capacity for the A to B or 1 to 2, node 1 to 2 or node A to B. And also for alternative 2, we have for A to B and B to A to balance the congestion, or yeah, we the both directions from B to A and A to B. For the alternative 3, we have added one lane also for B to A, and then also B to D. A to B, B to A, and B to D. So we have added one lane for 3 links. So and then also for the alternative 4, we have added another one lane or double the capacity for the A to F. Wait, I'll just share my screen as it is, so I can just go back to the Excel later. This one. So from A to V, B to A, B to uh wait, B to D, and also A to F. These are the scenarios or the links that we have identified. Then using a different link table for those 4 scenarios. And then we have tested it in the IFN. I mean, wait, wrong. In our IFN, the network is strongly connected, and our model used the total flow. We gathered 4,214 for the result of the base case. So going back to this one, you can see that the network for the from the last lesson, we like what Prof said, adding lane doesn't mean you're actually solving the congestion. You're just actually putting the congestion on a different link.
Somewhere else.
Yeah, and we can see this here from the I'll just discuss this from base scenario, the original 9.96% congestion level. When you add one lane to from A to B, it will um actually have a maximum congestion level of 10, but not necessarily on this link. And if you go to the alternative one, you can see that the congestion level for the node A to B and B to A to F decreases, but you have increased the congestion level for other links such as this nodes. That's the alternative one. And then going back to alternative 2, additional lane for A to B and B to A. So for both directions, this is it. A to B and B to A, or 1 to 2, 2 to 1. You can see that we have lessened from 9.962. We have, but we have just a slight changes in the congestion level here. So that's the alternative to adding one lane for both directions in that link. And then adding one lane for 3 links, you can see that same with alternative 2, it has this solution decreases the congestion level or the maximum congestion for alternative 2. So it becomes 9.08, and it didn't unlike from alternative 1, no link was compromised, or it didn't transfer the congestion to another link, or yeah, that's it. And then what if we add another link? I mean another capacity or another lane for another link, which is the A to F. You can see here that it actually decreases the congestion level for these links, but your maximum congestion increases from 9.96, it increases to 11.95%. So that proves that adding lanes doesn't really solve the congestion for a specific it can solve the congestion for a specific link, but it doesn't mean that it can solve the congestion or the maximum congestion for the whole network. Then going back to our presentation. Where's my presentation? So it's just we have put all of it here. So our recommendation on congestion changes is based on budgetary constraint and the consistent slashing of budgets uh, of of the budget um, for the national expenditure program, and then when it was approved to GAA, most of the budgets for the infrastructure is being slashed or being reduced. So for budgetary constraint, we have put different actions. The immediate action will be implement alternative one to quickly address the congestion on link A to B, providing immediate relief to the most critical. But since it is the most critical link, uh, that's the immediate action. But for medium term planning, we have to evaluate the benefits of alternative 2 for further improvements in both directions, considering a more balanced congestion reduction. And then um, we have opted not to include alternative 4 since it will just increase or the maximum congestion in the network. So for the long-term planning, we have to explore alternative 3 for comprehensive congestion management, especially if the congestion persists and resources allow for a more extensive upgrade. Um, So the recommendations prioritize addressing immediate concerns while we are considering long-term strategies for sustained improvements in the overall traffic flow, and considerations of budget, as I have said, available resources, and the urgency will play a crucial role in deciding which alternatives to prioritize and implement. So, regular monitoring and adaptability in planning are essential for the effective traffic management. And also, sir, if we have a better data set, we could have actually um, presented it better. It's just that the congestion level is too low, but you can see the difference, or for application purposes, you can see how the adding the solution or the alternatives is changing the results for or in the IM using IFN transport in the congestion level of different scenarios.
Okay.
That's it,
Okay,
sir.
so I think it's very nice, interesting, yeah, result. So, is there any question, comments, suggestion, probably from other groups? Anyone? Okay. Uh, uh, I just wonder, how do you get that 4,214?
Just
Very
added
low.
the total. Yeah, sir. We just added the total. I mean the peak hour factor result for
In the
all
whole
the links.
network?
Yes, sir, in the whole network.
But that's not include the uh, dummy links, no?
Ah, yes, sir. We have not yet included the mix.
Okay. Uh, have you ever considered, for example, because you already got the maximum congestion 1.06, right?
Yes,
Have
sir.
you ever considered to use that links to be that particular ring AP, right? To be 1.06, for example, you can adjust the FN to set the flow in order to make that particular link 1.06.
Ah, so we're just gonna use the maximum congestion level of 1.06, sir.
Yeah,
And
but
then,
that should be in that particular link, right? That you are based on the real data, right?
yes, sir. Based on the
Hmm.
real data.
So you can adjust that so that you can see the whole effect. And then once you calibrate the base scenario in order to get 106 consume congestion in that particular link, then you get the uh, what is that total flow in the network, right?
Okay, sir. That
Okay,
so
so
that will be the total flow once we have the 1
correct.
point. Okay.
That will be the
Okay,
total
got it,
flow,
sir.
and then you use for the other alternative scenario.
Yes, sir. So for the alternate scenario, we are going to use the total flow that we will be getting from the base scenario using the 1.06
Correct.
maximum congestion
Yes.
level.
So you adjust
Okay.
the flow in that base scenario in order to make that particular link 106, right?
Yes, sir. 1.06.
To fit with the data.
Yes, sir. Okay.
After that, so everything is the same. I think the result will be totally the same. Only
Yes, sir.
the number
Yes.
will be better, you know,
Yes, the
because
numbers
like
will be
9% congestion is very, very low.
very low. Yes, sir. I know.
Right. So I
Yeah.
mean the overall conclusion and the analysis will be the same. Only the numbers will scale up, right?
Yes, sir.
Okay.
So it's
Okay.
for scaling purposes. We will
Correct. Correct.
revise
So that
our
you because if the purpose is just what is that 0.9 9%, 10%, I think
that's it. Yes,
everyone
sir.
will love. Yeah. Okay.
Okay, sir.
And have you ever considered the microscopic analysis, for example, in the intersection to be more
Um
detailed?
not yet, sir. We actually just
Oh,
presented it since we are just trying to apply what we have learned from the
right,
IFN
right.
transport for
So,
easy
it,
referencing and easy
right,
time to present how it will affect the network
right, right.
using the IFN transport.
Okay. And last question is why do you use equal probability instead of, for example, capacity, the number of lanes?
Um, Sir, we use the equal probability here in the wait in the base traffic tracing just because here, sir, we have just used the probability of, for example, sir, from A going to B, that's
Mm-hmm.
B going to right.
Mm-hmm.
A going to right. I mean
Mm.
left. Ah, yeah, yeah.
To
And
the right.
then yeah, A to right, and then A through.
Mm.
So if you have an AADT of um 16,000, we have divided it zero point 0.5, the the total flow here is divided 50-50 for each node.
Okay, so what you have is only in the nodes A, B, C, D, E, F. That's the AATT.
Yes, sir.
Right? And then you want to know what is the traffic going here and there. You can use gravity
Yes.
model.
Gravity model, sir.
Yeah,
Okay,
the
sir.
right?
I just
Because you
noted
know
that.
the nodes and you want to know the distribution, right? That's exactly the
Okay, sir.
gravity model,
Gravity model and then max congestion,
right? Because you know the
total flow.
IADT there. Okay.
Okay, sir. This is all noted, sir. We will.
Okay, okay.
So maybe we could actually get a better data result number.
I hope.
I hope
Right,
using the gravity model. Okay, sir.
I hope. Yes. So
Thank you.
because you want to get the OD, right? Basically, what you want. Is that correct?
Yes, sir.
Hmm.
Thank you.
Thank you. Okay. Okay. So is that all? Any other group or any other particular person want to present? No more. Everyone already there, right? Okay. Thank you. Thank you for your uh, very nice presentation. Okay. So, and overall, I'm pleased with your work. Uh, so you can just revise it, improve, and then you publish it. Okay. Okay. So for today, wow. Okay. So we have a network optimization in the where is it? 1225A. I will show you the screen share. Right. So can you see? So we have discussed almost all of this, right? And then this is the last part of our class. Okay. So we discussed about three things: transshipment, traveling salesman, and map flow. Okay. So you can check this. Transshipment. Okay, here. Can you see my slide? Transshipment problem. Yeah. Okay. So, transshipment problem here. Okay, you have a very general okay, problem of network optimization. Okay, so in here you have a network connectivity with link costs. Okay, and each node is called transshipment node. That means either supply, demand, or both. Yeah? In IFN, we also have that transshipment nodes, right? Every node can receive, can also send some flow. Okay, but in this transshipment problem, they are not necessarily strongly connected. Yeah, so there are some supply node, there are some demand node. Which is supply node means they are source node. Okay, and there is also demand node, which is only sink node. Okay, of course, the source node will only send the flow. Okay, so we will use negative value, and then the sink node will also only receive. Okay? We will put the flow as positive. So in general, we call this transshipment node because it can send and receive. So there are three type of node: supply node, demand node, and transshipment node. Okay, either sink, source, or transshipment node, which is the normal node that we have in IFN. Okay, so now each link will have a cost to transport the item. Okay, now we are doing optimization problem. What is this? We want to minimize the cost, okay, of the flow. Okay, so you want to find the link flow to minimize the cost in order to balance the flow, similar to IFN. But in here, which is more general, we have also a supply and demand with this source and link. Okay. Here is the rule. Yeah? What is called balance of the flow rules. Okay. Now you want to apply the following balance flow rules in constructing the constraint for the minimum cost of network flow problem. So here is this table will be used, okay, in order to decide your rule that you will use. Okay, so when your total supply in the network is larger than the total demand, then this is the rule that you will use. Yeah, when you minus the inflow with the outflow, okay, then must be larger than the supply or the demand. When the total supply is less than the total demand, then in each node, inflow minus outflow will be less than total supply or the demand. In IFN, we have total supply equal to total demand, right? So in that case, the value is also equal. Okay. Again, when the total supply is less than the total demand, okay, then we know, okay, there's a problem that the total supply is actually less than the total demand. Then it's impossible to satisfy this all demand, right? So in that case, you use this in each node, okay, the inflow minus the outflow must be less than the supply or the demand. Okay. Now, when the total supply is larger than total demand, okay, in each node, you will put the total inflow minus the total outflow must be larger than either the supply or the demand. Okay. Now, the technique is simple. Okay. Now, let's define the node I or J. The link will be Ij, right? And then the link flow will be X, Ij. The link cost will be C. Yeah? So these are the X is the flow, C is the cost. Okay, then we can use the linear programming. We want to minimize the sum of link flow multiplied by the link cost. Now the problem is actually the flow constraint. Okay, so all the flow must be non-negative, can be zero, but not negative. Now, we define the flow constraint at its node, okay? So outlink will be negative, inlink will be positive, and then you apply the balance of the flow rule above, okay? So let's do the practice with the example so that you can understand, okay? First, look at this network. We have this in each node. We have either the demand or the supply. So this is negative. Right? This is positive in each node, and these are the costs. The link cost, okay, is given here. So in this example, which one is the source and which one is the sink?
Prof, the source node is G and the sink node is D.
Okay, so this is sink. Yeah, this is the source. Very good. Okay, so in the others are transshipment node. Yeah? That means they can receive and send. Right. So the source node can only send. The sink node can only receive. Okay, you can see this. Now, that is suppose these are the cities. Okay, 7 cities, right? And the demand we can put as plus, the supply can be put as negative, and then the link cost per car, okay, so this is for car manufacturer, are shown above. Yeah, and then now we want to decide what is the least costly way to transport all those cars because they are already in the port, right? Okay, so from A to G, okay, so what is the least costly way to transport the cars? This value in here is $30, that means per car. Okay, so my question to you, do you understand the problem or not? You have 7 cities, okay? Each city already have some demand or supply in terms of number of cars. You want to transport in order to balance this. Okay. The value to transport per car is given there. Say $30 or $40 per car. It's clear, yeah? I hope. If you have any question, you can ask.
Third question.
Yes, go.
How come in the one with the values,
Okay.
yeah, this one, because in the previous we tend to balance the amount. Like this is a sync node, G is a sync node. Why does it have a negative 300? But if you calculate the amount, it's only $145. What is the
This is
300?
given. This is given. Okay. So this value are given as our
Oh,
problem.
okay. So it's not like the previous that it has to balance itself out. That what
No,
it
no.
receives is
Our
different.
problem is to minimize the transport cost. We decide the flow
Mm.
in order to minimize the transport cost. So this is totally different problem from IFN.
But what does the negative 300, negative 200?
Positive negative is given here. So demand is positive, supply is
Oh,
negative.
okay, okay, okay,
Yeah,
okay.
is it clear?
But
So
but but
demand
it,
is
but it's G is
yes.
supposed to be a sync node. It's supposed to be a source node, right? So why does
C
it
is
have
supposed to be
G?
the source node. Yeah.
Letter G is supposed to be a source node. So why does it have a demand of 300 if it cannot receive?
Negative. Negative is supply.
Yeah, but it cannot receive. It cannot receive, right?
Correct.
So it's a
Cannot receive.
demand.
So
Supply.
in
Why why negative
point
300?
G, okay, node G is source node. It
Yes.
can supply the
Uh-huh.
number of cars. Okay, it has 300 cars there. Negative there
Okay.
meaning they have 300 cars there in G right now.
Okay. And then the
Okay,
dollars
and
is the cost of the
the
supply
cost
per
per
car.
car to transport
Ah,
per car. Okay,
okay.
here 80 here, that means they need additional 80 cars in
Okay.
city D.
Okay.
Clear?
Thank you, sir.
Okay,
So this was
negative
the
here is
part.
supply.
Okay.
Okay.
Okay. Thank you, sir.
Positive here is demand. I hope it is clear. So in node E here, positive 170, that means they demand 170. Clear, yeah? Okay, so when the problem is clear, now we need to check, okay, which balance of flow rule we will use. Remember, there are three, right? So larger or smaller or equal, right? So then we compute. Okay, so the total demand or all the positive you add, okay, and then all the negative you add. Okay, so in here, so negative 300, negative 200. Yeah, so this now become 500 total, right? So the positive you add, okay, the negative you add. Oh, so now you know that the total supply is larger than the total demand. Then we will use, okay, based on this table a while ago, right? We will use this rule, okay? So we will use this rule because, okay, the total supply is larger than the total demand. Up to here, is it clear or not? We will use this rule in each node. Okay, why? Because the total supply is larger than the total demand. Okay, okay, let's apply this. Okay, so the actual formula of transshipment is like this. You want to find the flow, link flow, this one, Ij is the link, and then you want to minimize the multiplication between the flow and the cost. Yeah, and then you sum all links, right? Subject to constraint, what? The total flow, yeah, the total flow here must be larger than the total kappa here. Yeah, so this is the total of all nodes, right? Either supply or demand. Okay. In this case, the total flow is larger than zero in this case. Nah? in your case because the supply is larger than demand. Okay, supply is negative. So, of course, all flow must be positive. Okay, so in that case, now you go to each node. Okay, you go to each node. In your slide, can you open this drawing? When you download the slide, can you open this drawing? Yeah. When we are offline, I will draw this drawing in the whiteboard. Okay. So can you put this drawing so that you can understand what I'm talking? In your computer, open this drawing. Okay. Now I will show you this. So in node A, can you see? Okay. We have negative XAB minus negative XAD. Okay, must be larger than minus 200. Do you understand the meaning? Okay, AB, AD. Let's go to node A here. Here. In node A, this is actually a source node, right? So going to AB and then going to AD. Okay. When going out, we put it as negative. Yeah. When you go out, you put as negative. Here, outlink is negative. Is it clear? Okay, so in node A, you have negative AB and then XAB and then negative XAD. Okay, and then what is the value? Negative 200. Yeah, this is the node value here. And then the sign come from the flow balance a while ago. Yeah, this one. The sign come from here. Positive, larger than or equal. Okay, there. Okay, you have A, B, and A, D, and then this is the sign from the flow balance, and then this is the value for the node. Clear or not? Okay, if you want to make this positive, so you just multiply everything with -1. So if you multiply by -1, the sign is also less than. Instead of larger than, you can make it less than. In node P, the same. Yeah. You look at this. This is positive. This is negative. Why? This is outflow. This is inflow. Can you check in your network? AB and BC. Yeah, in the network, in node P here. AB is inflow. Yeah, BC is outflow, and then the value is 100. Yeah, it's not equal because the total supply is larger than total demand, so it must be larger or equal. Yeah, is it clear or not? Up to here. Okay, so with this you can continue for all nodes. Yeah, so you can continue for all nodes. You can create this result. Okay, so you want to minimize, okay, the value, which is 30 times XAB, right? And then here AD is 40. This is the cost time the flow XAD. Okay, and then and so on until all links, and then subject to, for each node you create the balance of the flow. Okay, up to here, is there any question? Can you make this or not? Any question? Comment probably. So once you make this, you can just put it into Excel. Yeah? Okay. So the yellow here, I just put anything one. Yeah, these are the flow. And then the cost, this is the one that you type. And you have the node constraint, right? The left-hand side is the one that you put based on that formula here. Okay. The right-hand side is just this number. You can put it in. Okay. And there is a surplus of minus 20. And then after that, you just use solver. Okay. You want to minimize, okay, the objective value, yeah, is Z, is multiplication between the flow and the cost. And then you sum some product, right? Yes, Katrina, you want to ask question?
Prof, is it correct that the left-hand side is the sum of the coefficients?
The left-hand side is this one. For example, minus XAB minus XAD.
Okay.
So this is the flow.
Okay.
So you point equal to that flow XAB and then minus again with XAD.
Okay.
And then for point B, this one positive and negative of this.
0. And then 1.
Yeah, at this point is 0 because this is 1 and 1, right? This is minus 2 supposed to be
Mm-hmm. Okay, Prof.
because everything is 1 in here, right?
Okay.
So, okay. And so the left-hand side is actually the most difficult part there because you need to put it one by one, okay, based on this constraint. So, but this constraint is easy, right? Actually, outlink is negative, inlink is positive. That's it. Okay, you need to formulate this. For example, in node E here, can you see? Node E here, what is the inlink? Inlink is CE, right? And then FE here, and then GE, yeah? And then outlink is ED, right? And then EC, and then EF, yeah. So, yes, Marie Grace.
Sir, but like for example in A, if this is -2, how can the formula be correct that -2 is greater than or equal to yeah, it's
Not yet. This is just initial value, okay?
okay.
Later we will do using solver.
Okay.
Initial value, you set all 1, right?
Uh-huh.
When you use solver, okay, this initial value -2 and so on, these are because you put the flow all 1.
Oh, okay. Okay.
Okay, so this is just initial value. Once you set up this constraint and the flow and make this positive, right? Non-negative, and then you solve, then you will get this value. With this is the result. So this is the optimum value, which is nice. You see, for example, ED, you don't need to have any flow. Okay. GE, so these are the flow that you actually put in. So I put this flow here into the back to the network. Then you will see the solution. Yeah. So I will transport 120 from A to B, yeah, and then 80 from A to D. Right here, from B, I will transport 20 to C, okay, and then 40 from E to C, yeah, and then 210 from G to E, and then 70 from G to F. These are the solution, yeah. The one in red here, I put a solution. So there is no need to transport from G to D, for example. So this is the optimum solution. So this is very nice for logistic, isn't it? If you want to transport things from one port to another, from one center to another. So this is very useful model. I know this is not necessarily transport for the government, but this is one day what some of you may work in the logistic company, right?
Yes.
And then you know the solution already.
For business, it's very important. So.
This is very important for business, correct?
For big businesses, sir, like for example, I used to work for Emperador, one of the
Uh-huh.
distillery
Right.
here in the country.
Okay.
Um I've been the one assigned in transporting or assigning the right
Yeah,
shipments for molasses. If your
right.
molasses is the raw materials that we use
Uh-huh.
to convert or to extract the alcohol for making
Okay.
alcohol drinks like Emperador.
Right,
So
right,
it cost them millions of money just to transport
right,
um
correct.
a specific amount of the raw materials. That's
Right.
why I actually know
I think
this
this is
technique.
very important, right?
Yes.
This kind of model is very important for this kind of problem. Yeah. So this is you will use this like day to day working condition when you work in that kind of company. So this is your problem every day, okay? Because you need to assign how many today for this particular demand and supply. Okay, and this is very nice because this is the optimum solution. Yeah, optimum mean this is the best in terms of the minimize the cost. Okay, no other best. Okay, so I hope this is useful for you. Yeah. Uh, Next part. So when we do the last time we do the shortest part, right? So I want just to link back. Yeah? When we do the shortest part, that's exactly the same as transshipment. I said here. Yeah? They use the same technique as transshipment problem. Okay. The only difference is this is actually simpler. Why? Because you only use one unit flow from the source to the sink. You already did this last time as your assignment, right? So exactly the same. Yeah. Transshipment is actually more general. Yeah. Even more general than IFN. Okay. The last but not least, okay, I don't know if you are going to work for the piping company. Okay, for example, pipe of the gas, pipe of the uh, water, or probably pipe of the oil. Yeah, so this is the problem that you need to solve, which is called maximum flow problem. Yeah, so the problem is this: yeah? You have a source, okay, where the origin, and then you have the sink. Okay, and then now each link have capacity, which is physical capacity means the maximum flow that can pass through that link. Okay. Now the question is, uh, determine the maximum flow that can pass the whole network. You know the capacity on each link. Now question is, for this network, what is the capacity of the network? Okay. Uh, it has no supply and demand node actually, but it has only source and sink. Okay. So again, the application is for oil, gas, water, and so on. This is pipeline. Okay. Well, you can use it for transportation to determine the maximum number of car that can travel for the whole collection of the street, right? So each street will have capacity in terms of number of lanes and the speed limit and so on. So these are the application. We want to know the network capacity. Okay, so given here is the value of, for example, this three mean three, capacity is three, okay, flow, yeah, in terms of the flow. So can be 3 liters, can be 3 cubic meter, can be whatever value that you put. This is just uh, or the number of lanes probably. Okay, so this is just capacity. Capacity means maximum flow. Okay, now you have the maximum capacity on its link. We want to know the maximum flow that can pass the whole network from A to D. Okay, so the solution is actually similar to transshipment problem. Okay, but The technique is actually to create strongly connected network, become IFN. Okay, so you need to connect the uh, the source and the sink node, yeah, okay, with some dummy link like this. Okay, and then you can solve the maximum problem as transshipment problem now. Okay, remember each node now have uh, zero flow because no demand, no supply. Okay, so that again the same technique as a while ago. Okay, what you want to get is actually the maximum flow in that dummy links here. XDA. This is the maximum flow for the network. So that's the meaning of dummy links here. Okay. And the technique is the same. Okay. You put in is positive, out is negative. But remember, because we don't have demand and supply, so everything is equal to 0. Right? And then you have the capacity here. So that means the value of flow of XAB is between 0 to 3. That's the capacity. So you put the capacity as a constraint, and then the capacity of this dummy link is an infinite. Okay. Then you just put this into Excel as usual. Okay. And capacity is infinite for XDA, and then you use solver, the same thing, and then you will get that value is 7 in the example. So that means the whole network, okay, can only accommodate 7 units of flow. Okay. Is there any question up to here? So we want to know the capacity of the whole network instead of given the link capacity, how many cars in transportation, yeah, how many cars can we accommodate in the whole networks? You can calculate using this technique. If you want to know, for example, you want to get gas or oil, right, from the source of the mining up to all the distribution. Okay, so through all these different network of pipeline, then you want to ask how many liter or how many barrel can we pass this oil? Yeah. So network capacity. Okay, so with this, I think you can face your final exam. Thank you very much for the semester.
Thank you so much, sir.
Thank you so much, sir.
Yeah.
Sir,
Thank you, sir.
same procedure again for the final exam. You'll open the exam for the whole day. I mean,
Yes, the
okay.
exam is the whole day. Now, question is how many
Attempts.
items I ask you now.
3. 3.
You want 3?
Customer.
Okay, so if you have more than one attempt, so I will hide the answer first. Okay, that means I will open the answer the following day. Is that okay?
Yes, sir.
Yes, sir.
Okay,
Yes, sir.
so
Thank you.
you will get the grade at the same after you submitted all the exam,
Yes, sir.
only the grade, but you don't see the answer. No problem, yeah. So because exam is open from morning until night, okay.
Yeah.
So you can take any time.
And then it's
3
the same
attempts.
for the highest score.
Of course, highest score, no problem. So,
Sir,
so
to
if you didn't
clarify,
submit the paper, sorry,
sorry, sir. Sir, sorry, to clarify again, the deduction for the wrong answer is 10%.
for the
10%
yeah,
for
so 10% deduction. So in that case, if you answer all, you will surely get very good grade already. Okay, so the purpose is to make you higher grade rather than just a standard grade.
That will be my third
So,
attempt.
but you don't know each attempt you don't know what is the grade.
Okay, sir.
Right. So, what else? Okay, so if you have not submitted the paper and the presentation, so please submit it. Deduction 2 per day, right? So up to the date of the final exam. If you have also some assignment that you did not make yet last time, so please submit it up to the January 12th. Okay, so on January 13, I will compute everything and then I will post the grade computation in Moodle as Excel file. Okay, and then you can protest up to maybe 15 if you want to ask question. And if my computation is not correct, you can protest, no problem. And then after 15, I will submit it to the OGS. Okay, then you have no right to protest anymore. Okay, okay. I think it's fair enough, right?
Sir, but if we have submitted already, but you ask us to edit our paper and our
Please edit, and then you can get higher grade.
Okay, sir.
Okay, and aside from this class, so my goal is to encourage you to publish your work. Okay, you will not get grade from that, but you will get your own fame anyway. You don't need to include my name, no problem. Just publish it on your own. Okay, it will be your benefit, not mine. Okay, thank you very much for the semester, and I hope we can meet again somewhere, somewhen.
Okay, sir. Sir, is it
Okay.
possible if for the thesis purposes, we can get you as our advisor?
Uh, I will be happy to do so. Okay, but whether it's possible or not, that's depends on UP.
Okay, sir.
All
Thank
right.
you.
So from my side, I'm okay. So,
Okay, sir.
but they allow or not, I don't know.
Okay, sir. Well,
You
but it's
need to
okay
ask them.
to consult and
Sure.
yeah.
Consult is anytime. Okay, you don't need to put me as advisor, or you can consult anytime. No problem.
Okay, sir.
So there are many people from other countries, not just the film. For example, from India, from Russia. They ask, no problem, no. Okay, they don't even know me, so they just see the website and they ask. So no problem.
Yes, sir. And
Okay.
also, sir, just to
Mm.
remind them that the Moodle, I think we have an access for at least a year, right?
Yeah. So the model is accessible up to next year. Okay. Uh, well, 6 more months, no?
Okay, sir.
Before
Six more
the next
months.
semester. Okay, because this is already one semester. So I one semester off, and then the next semester I will delete to accommodate 10 new students.
Okay, sir.
Right.
Thank
But
you.
you can download anytime, and then the lab is already public. The one in Revoledo,
Yes,
the
sir.
lab's all public, so you don't need to worry. I will keep updating. And if you have any critiques, any suggestion, I will be happy to improve myself. Okay. So thank you very much.
Yeah. Thank you, sir, and thank you for your
Yes.
generosity to us in granting.
It's nothing.
Thank you.
Okay. So by submission only you get 100 whether you are right or wrong. So in the assignment. So please submit it on time. Okay. I will just keep comment to improve. You submit it again, it will go up. But you tell me, yeah, I don't know which one because so many, right? So you need to tell me, okay, which one I need to regrade. Okay, so thank you very much.
Thank you very much, sir.
Thank you, sir.
Thank you, sir.
Uh,
Thank you po.